The notes are linked on Schoology. If you scroll all the way at the bottom, you'll see it all the way at the bottom. The notes are linked on Schoology. Okay, we're live on YouTube. So, slope fields. What are they? A slope field is basically a graphical representation of a differential equation. So it shows all of the different slopes that are represented by that equation, the differential equation. And it's seen as a graph with short little segments. So each little segment represents the slope at that particular point in time. So it's basically just a bunch of tangent lines, right? But just not continuous. We're kind of just cutting off each tangent line along the graph. And so its slope is determined by plugging into the derivative at the midpoint of the segment. We're going to see kind of what that means in just a second here. And so why is this important? Because we can go ahead and solve differential equations, but it's nice to be able to see the graph, and you're going to see kind of what I mean by that, how when we look at the slope fields, how it looks when we kind of have it all graphed out. And so it kind of helps us to see patterns a lot more easily. So let's just jump into this part right here. We have here a differentiable function, which means obviously it's differentiable. So it has a tangent line at every single point. We can find the slope at every single point. So what we're going to do is draw some small pieces of some of these tangent lines along this function. So this is the function, it's a polynomial x cubed plus x squared minus x plus 2. So what we'll just kind of quickly do is I just pick any point. So for example, right here, there's a point. So I'll draw a little line segment representing the tangent line. So something like that follows the natural slope of the curve. And then maybe I'll skip a next value, jump here. And then there's another tangent line. And then maybe let's do one here. That's our next tangent line. I'm picking kind of specific x values, but we can just kind of pick any random x value and draw a tangent line, just a little line segment. And we can draw kind of shorter segments so we can fit more along the curve. So we're looking at these little segments, and you can see how each segment, if you have them kind of small enough, they pretty much almost create the shape of the graph. So that's what I mean by it helps us to visualize equations, and it helps us to see patterns along the way. So let's go ahead and jump into an example here. So we're going to consider the differential equation f prime of x is equal to 2x. And we're going to sketch the slope field in the graph below. So the slope field is going to be the little line segments of slopes, but we need to just kind of set up a way of organizing everything. So we're going to make a table here. And we're going to have the point. Oh, I lost my place. Is this the right problem? Yeah, example. And then the slope that goes along with it. So what this means is we have this rate of change, right? dy over dx, I can write it like that, is equal to 2x. So with the point, let's say we start with the point 0, 0. We can figure out what the slope has to be at that point by plugging in those x and y values. In this case, our derivative is 2x, so we only need to plug in the x value. And when we plug in 0 for x, we get 2 times 0, which is 0. So what I will do on my graph here is where I have the point 0, 0, I'm going to draw a slope of 0. And then we're going to pick another point. I need to write something down here real quick. Okay. Let's pick the point 0, 1. So 0, 1 means I'm going to plug that into the derivative again. The x value is still 0, so when I plug it in, I'm still going to get a slope of 0. And so that means at the point 0, 1, which is right here, I'm going to have a slope of 0. And we're going to do that. We're going to do a 3 by 3 kind of matrix on here. So that means we're going to go up to 3, and then over to the side to 3, and also on the negative side to -3, and then down to -3. So we're going to do all of those points, and then all the points in between. So we're going to go out as far as, oops, not that far, -3, 3, and then as far as 3, 3, -3, 3, and oops, -3, -3. Okay, and all the points in between. So that means we still need 0, 2, which means we're still going to have a slope of 0 because of this x coordinate. Our derivative is only affected by x. So if these all have the same x coordinate, that means they're all going to have the same slope. So at the point 0, 2, another horizontal line segment because it has a slope of 0. And I can already go ahead and assume it's going to be the same all the way down because I know that those all have the same x coordinate. And so that's the only thing affecting that slope. So I'll do one more. 0, 3. We know that's 0. Okay. But all the other points that I already filled in, right, we know that's going to be true. We'll do kind of another table here and just kind of pick more points. So let's pick the point 1, 0. That's going to be this point right here. Well, now the x coordinate is 1. So when I plug that into my derivative here, 2 times 1 is 2. So now this point has a slope of 2. So when I come over here, you can kind of eyeball it in this case. I'm going to do a slope. Sometimes actually what I do is kind of visualize, right? A slope of 2 would mean up 2 over 1. So it would look kind of like that. So that kind of gives me an exact kind of slope there. Kind of, sort of. So you can kind of visualize what that slope would look like and then get your line segment from there. So that is a slope of 2 for that little segment. And then, like we kind of pointed out, all the points that have the same x coordinate. So even if I go to 1, comma, -1, I know it's going to have a slope of 2 because of the derivative that we're working with. So I know that this is going to look kind of like this. Okay. And we'll move on to the next one. We'll just do a couple more, and then by then, actually by now, I'm sure you probably have the pattern figured out, but we'll just do one. So on the other side, let's do -1, 0. So that means our slope will be -2. So it's going to be a negative slope, but the same kind of slope as we have on the other side, just in the negative direction. So we know that that's going to be true all the way through here. This one is maybe a little too slanted. Okay. All right. Next row or column, whatever it's called. When x is 2, that means our slope is going to be 4. So it's going to be a lot steeper. Oops. It's going to look something like that. We know that's going to be true for all values of coordinates 2 here. And then on the other side, we know it's going to be -4 because we're plugging in -2. So my sketch is becoming a little rougher and rougher, but that's okay. We kind of can start to picture what kind of a graph this is. Like you can see what does this graph look like? It's a parabola, right? So we're going to do the 3's really quickly. 3, when we plug in x value of 3, that would mean 2 times 3 is 6. So it's going to be a lot steeper. I would say even almost to the point of like, maybe not like vertical, but it's getting steep. And for the purpose of our visualization of the graph, I am going to make it like pretty steep kind of looking. So we can try to differentiate. Actually, I would say it's getting pretty close to vertical. Differentiate between a slope of 4 and then a slope of 6, right? It's going to be a lot steeper. And then same thing on the other side. Differentiate between -4 and then -6 is going to be steeper still. Oh, don't want an ellipse. Okay, so there is what we call a slope field. So the slope field, if you're given a derivative, you can pick points, plug it into the derivative. That's going to give you the slope at each particular point. And so once you have the slope at each particular point, and if you graph those, if you have enough points to then take a step back and look at what kind of shape it's created. And you can see it's created kind of this pattern that looks like a parabola. So what I'm going to do is, and it says here for example B, sketch 2 different graphs given that the solution passes through 0, 0 and 1, 3. So that means if you look at this field, I can draw different parabolas based on different points here. So like for example here, I can draw a parabola with this kind of vertex at 0, -2. and then draw it out that way. Or I can pick a different vertex. I can pick the vertex 0, 1. And then that would mean I have a parabola like that if you follow the graph. Or I can pick 0, 0 as my vertex. And that would mean I have a parabola that looks like that. So hopefully what we're seeing here is that there are lots of possibilities of parabolas here. Actually, I'll draw in all these possibilities here. Right. The only difference is a vertical shift, right? So before we jump into that, sorry, I'm kind of like skipping ahead. Back to the problem. Sketch two different graphs given that the solution passes through the point 0, 0. So actually, I've drawn it in here. I'm going to do it in a different color now. Let's do it in pink. So the point 0, 0 is right here. So it's actually going to be this parabola that we see drawn right there. 1, 3, let's do it in orange, is a point right up here. So I can see that it's going to be this parabola that I drew right here. That is going to go through that specific point. So with this kind of example, what we just did was we were given two different solution points, right? And this should remind you of what happens when we try to find the solution when we do the separation of variables, right? When we take dy over dx and we separate it, and then we integrate it, and so we would get y equals x squared plus c. And then the only way to figure out what c is if you know a point, right? So in this case, if we know that the point 0, 0 is on there, then we could plug that in. We know that our c is equal to 0. So then we know that our equation would be y is equal to x squared. And take a look here. Look at what we have in pink. That's the one going through 0, 0. What is the equation of that parabola? It's y equal to x squared, right? Let's take the point 1, 3, and let's plug that into our general solution here. So our 3 is y, x is 1. So c would have to equal 2. So that means our particular solution for the equation is y is equal to x squared plus 2. And if you look at our orange graph, that's the one that's going through the point 1, 3. Look at its vertical shift. It's gone from x squared up to x squared plus 2. So the slope field is a way for us to visually figure out what those particular solutions are, right? We can see the general solution. We can see it's in general x squared, which is why, right, we have this general solution here, x squared plus c. But we have a variation of plus c's. Plus c represents the vertical shift, right? So we have a variation of all of those vertical shifts. And if we were to kind of, keep it going, we would still have an infinite number of possibilities for c. And the only way to get a particular solution is if we know a specific point that lands on that equation. Once you know that point, you can plug it in and then find that particular solution. Or once you find that point, you can plot it and then follow the slopes to get a particular equation from the graph. So in this case, we found the equation, f of x is equal to x squared for 0, 0, and f of x is equal to x squared plus 2 from 1, 3. We did that using integration, right? But now we're seeing that's not necessarily the only way. We use the slope field, we can determine those equations as well, just by looking at it, knowing your parent functions, and then going from there. All right, let me know if you have any questions along the way. I'll be checking the group chat here. And let's see how much time we have. 15 minutes, awesome. We will do another example. So here we have the differential equation, which should have a prime here. Sorry, typo. F prime of x is equal to x plus y. So this time our differential equation involves both x and y. So we're going to see it's a little bit more interesting when we plug in points. So let's go ahead and do that. And we're going to do the same thing. We're going to go as far as 3. We'll do like a 3 by 3 little matrix here. So there's our border points. And we're going to do all the points in between as well. So instead of doing the table, I'll show you another way that I like to kind of organize all my information. And that's just to kind of pick the points here. So let's start. Actually, yeah, let's just do, instead of going, let's just go up to 2. We'll be working with fewer points, but that's okay. We'll still get a good idea of what's going on here. And let's do 2 by 2. Okay. So -2, -1, -2, 0, -2, 1, -2, 2. Oh, I skipped -2, 2. Or -2, -2. Okay. So those are all the points with the same x value. But when I plug it in to the differential equation here, that's going to give me -3 as a slope, because -2 minus 1. Then the -2 plus 0 is -2. -2 plus 1 is -1. -2 plus 2 is 0. And -2 minus 2 is -4. Okay. So I can go to all these points here. -2, 0 is -2, so it's going to be a downwards, since it's negative slope. And -2, -1 is -3. It's going to be a little bit steeper than the one that I just drew. And then -2, -2 is -4, so it's going to be even more steep. Okay. These are just kind of rough sketches, so it may be a little off, but we get kind of a good idea. Okay. -2, 1 is -1, so it's not as steep as the one right below it. And then we get to -2, 2, which is 0. So there we have kind of the progression. We see that one column is not going to do enough for us to get the full picture. So then let's jump over to -1. So we've got -1, 2, -1, 1, -1, 0, -1, -1, and -1, -2. So we plug these in. -1 plus 2 will be 1. -1 plus 1 is 0. -1, -2, and -3. So now I go to the points and I plot out those slopes. So now we actually have a +1 slope. That's different there. And then -1, 1 is horizontal. -1, 0 is -1. And then it gets a little bit steeper with -2, and then just a little bit steeper with -3. Okay, so we're starting to see some kind of a pattern emerging, hopefully. Then the next one. I know this kind of feels repetitive, but it's part of the process. Oh, I keep just doing all of these out of order. 0, -2, 0, -1, 0, 0, 0, 1, 0, 2. Okay, plug in here. That's going to give us -2, -1, 0, 1, and 2. So this has a -2 slope. Say something like that. Then -1, 0 at 0, 0. And then 0, negative, oh wait, no. +1, and then +2. Okay, so we're seeing some kind of pattern going on. We'll keep going. Oh. -1. Okay, so we get -1, 0, 1, 2, and 3. And then we come back. -1. Oh, I did these. -1, 0, 1, 2, 3, and then the last one, 2, 2. So that's going to be 0. That's going to be 1, 2, 3, and 4. So they actually all end up being positive at this point. We have 0 down here, +1, +2, +3, +4. Kind of really exaggerated those last couple ones, but that's okay. Actually, let me just, okay. So this may look kind of weird, but we should kind of start to see a little bit of a pattern. So if our tangent lines, when you look at them, they kind of all end up lining up, which we can see here. Aside from this one's kind of off. Should kind of match up with all the rest of them. See how these all make one kind of straight line there? That means we've come across an asymptote. We have a straight line there, so we know that this is like a slanted asymptote. So it helps us to kind of get a picture of what's going on. Part B says, sketch two different graphs given that the solution passes through 1, -3 and 1, 3. So let's start with 1, -3. Oh, of course I didn't read this. Duh, we should have gone down. That's okay. 1, -3 will be right here. And our tangent line at that point is going to be -2. So it's going to look kind of like that. Okay. So if I were to try to visualize going through this point and following, we can kind of see that it's following really closely to that asymptote. So that would be what our curve looks like going through the point 1, -3. And then going through the point 1, 3, of course I tried to do a shortcut and do 2 by 2 and then do the actual problem going up to 3. So the slope here would be +4. So it'd be really kind of steep like that. And the graph that we've kind of created here kind of follows like that. We can see how the slope at that point is kind of leading down to this segment, and then that segment is leading us towards the asymptote, but the asymptote we can't cross, right? So it's just going to get really, really close to that and then just kind of follow in that direction there. Okay. All right. Last kind of short section here that we'll do really quickly. A little matching. So it says match the following slope fields to the differential equations. So we have y prime is equal to x plus y prime is equal to 2x, and then y prime is equal to y. So remember, we're not looking to see this graph on here, right? Like 2x, I'm not looking to see just a line, a diagonal line. No, this is representing the slope all along, right? So I could pick specific points. Here, for example, with 2x, I know that all of my x values are going to be affected the same way, right? So if I plug in an x value of 0, then I'm expecting to have a slope of 0. So if I look at these graphs here, like starting here, and looking at when x is equal to 0, are all of those slopes 0? No. We have one slope of 0 here, but then we have, you see it's kind of growing and then decreasing. So this would not work out for us for B. If we look at this graph, when x is equal to 0, again, we have varying slopes. It's not a slope of 0 all the way through. So this would not work out for us. And the last one, here we do have a slope of 0 all the way through. So since that is our only option here, we're going to go ahead and match those two to each other. Okay. Next, let's take a look at, let's see y prime equal to y. So that would mean the y is dependent, right? It doesn't necessarily matter what x is. The derivative is, or the slope is based off of y, and it's going to be equal to y. So if I pick a y value, for example here, I should see that the slope is the same all the way through. So in this case, y should equal whatever this y value is, 1/2, right? So it's a half slope all the way through. Here, y is equal to 2, so it's a slope of 2 through. So that matches for us. If we notice here, this does not have the same slope all the way through. So this 2 here would be a correct match. And these two here, obviously by process of elimination, would match. If you wanted to double check it, you can pick any point that you want, any random point, plug it in here, and double check that the slope looks to be reasonable for that output. Okay. So that is slope fields. I'll post a little video kind of doing this example for you all, since that's the last one that we have here. And then I will also post the assignment. It's several problems having to do with growth decay and slope fields, and you'll work on that for going into next week. And next week we start reviewing. So please let me know if you have any questions, but if not, I hope you all have a great rest of your day. Have a wonderful weekend, and I will see you all on Monday.